observations, it becomes stochastic gradient descent. And in this case, the only information you're using is a single misclassified observation. So really, the perceptron learning algorithm was all the way along just gradient descent or stochastic gradient descent in disguise. Okay, so very interesting. Yeah, we've got a multi-class perceptron learning algorithm. That's what it looks like. You're welcome to read this. Don't worry, you don't need to know this. But yeah, okay. Now I can show you finally my video.
It all starts with artificial intelligence.
A machine has been programmed to see and to move objects.
AI isn't new. The term was coined back in 1956. In 1958, Cornell University psychologist Frank Rosenblatt built the perceptron, designed to mimic how neurons fire in our brains. So here's a basic model of how neurons in our brains work. An individual neuron can either fire or not. So its level of activation can be represented as a 1 or a 0. The input to one neuron is the output from a bunch of other neurons. But the strength of these connections between neurons varies, so each one can be given a different weight. Some connections are excitatory, so they have positive weights, while others are inhibitory, so they have negative weights. And the way to figure out whether a particular neuron fires is to take the activation of each input neuron and multiply it by its weight, and then add these all together. If their sum is greater than some number, called the bias, then the neuron fires. But if it's less than that, the neuron doesn't fire. As input, Rosenblatt's perceptron had 400 photocells arranged in a square grid to capture a 20 by 20 pixel image. You can think of each pixel as an input neuron, with its activation being the brightness of the pixel. Although, strictly speaking, the activation should be either 0 or 1, we can let it take any value between 0 and 1. All of these neurons are connected to a single output neuron, each via its own adjustable weight. So to see if the output neuron will fire, you multiply the activation of each neuron by its weight and add them together. This is essentially a vector dot product. If the answer is larger than the bias, the neuron fires, and if not, it doesn't. Now, the goal of the perceptron was to reliably distinguish between two images, like a rectangle and a circle. For example, the output neuron could always fire when presented with a circle, but never when presented with a rectangle. To achieve this, the perceptron had to be trained, that is, shown a series of different circles and rectangles, and have its weights adjusted accordingly. We can visualize the weights as an image, since there's a unique weight for each pixel of the image. Initially, Rosenblatt set all the weights to 0. If the perceptron's output is correct, for example, here it's shown a rectangle and the output neuron doesn't fire, no change is made to the weights. But if it's wrong, then the weights are adjusted. The algorithm for updating the weights is remarkably simple. Here, the output neuron didn't fire when it was supposed to because it was shown a circle. So to modify the weights, you simply add the input activations to the weights. If the output neuron fires when it shouldn't, like here when shown a rectangle, well then you subtract the input activations from the weights. And you keep doing this until the perceptron correctly identifies all the training images. It was shown that this algorithm will always converge so long as it's possible to map the two categories into distinct groups. The perceptron was capable of distinguishing between different shapes like rectangles and triangles, or between different letters. And according to Rosenblatt, it could even tell the difference between cats and dogs. He said the machine was capable of what amounts to original thought. And the media lapped it up. The New York Times called the perceptron the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence.
After training on lots of examples, it's given new faces it has never seen, and is able to successfully distinguish male from female. It has learned,
In reality, the perceptron was pretty limited in what it could do. It could not, in fact, tell apart dogs from cats. This and other critiques were raised in a book by MIT giants Minsky and Papert in 1969. And that led to a bust period for artificial neural networks and AI in general. It's known as the first AI winter. Rosenblatt did not survive this winter. He drowned while sailing in Chesapeake Bay on his 43rd birthday.
The MATLAB is a roadworthy truck, modified so that researchers or computers can control the vehicle as occasion demands.
Okay, so you can watch the rest of the video. It's pretty interesting. It's more about actually processing these complicated dot products and stuff. But yeah, you'll see. It's like, let's go on like self-driving cars and these kind of things. So again, a lot of the things that you see today, very old ideas and machinery built on all stuff. But yeah, so that's the perceptron learning algorithm. And yeah, very interesting that the guys that were working on this technology way back when were also sort of, I guess, swept up by the metaphor and the hype, thinking that these things could think because they were simply inspired by these biological neurons. Now, when you actually go and try and build a normal neuron, I guess, and you read the modern literature, you can see that, well, this is quite more involved than what we, this summing and then firing thing, that is not even closely approximate what a neuron does. They're much more general than that, and there's also a whole time dimension which you need to account for, and threshold potentials, these kind of things. Okay, but where does this put us? Okay, so usually what I would do then is I would code up this algorithm, so the master's machine learning will do that. I'll show you how to code up this algorithm, and then we're going to ask the question, why was Rosenblatt fooled by this algorithm? Okay, what we're going to go as follows. So, got an example data set. You don't have to know any of this code. I'm just going to show you some pictures, and we're going to okay. So what I do is I set up then my own experiment. So he was looking at dogs and cats and how these things could, how these models could actually distinguish between that. So I set up some data set just to give you some idea of what the data set would look like. Mine is a bit more simple. I picked like, I've got a response, one of three categories. So the Y's are encoded as 1, 2, or 3. And then I've got a bunch of pixels. These are sort of 10 by 10 pixel images. I'll show you what they look like now. So maybe simpler pictures. Add some noise, and then this is what our data set would look like. And then we try and get this. There you go. So this is what our data would look like. I've got squares, I've got donuts, and then I've got hearts. Okay. So I'm trying to mimic here what a picture would look like. So what is a picture again? Well, you've just got a bunch of cells, and in each cell you've got a pixel intensity. So I set up some simulation scheme which simulates a picture, so like photons hit each one of these boxes and counts that, and that's how a picture is constructed. Okay, so not perfect images, slightly noisy. Now, first thing we need to notice is, okay, maybe I should ask you this. These patterns, are they linear or are they non-linear? Would you say they are non-linear? Hands for non-linear? Yes. Why? Why would you say that they are non-linear? Where do we define typically as linear? We've got a function in mind, right? So we just have some parameter multiplied by something, and then that's a value. So the reason we would be tempted to call this linear or non-linear is, well, what's the equation even for a rectangle? What's the equation for a donut? What's the equation for a heart? Okay, you can write down an equation on a two-dimensional space, but there's something else happening here. These inputs, what are the dimensions of these inputs? So you've got a 2 by 2 image, but the actual input is what? 10 by 10, it's got 100. You've got a 100 dimensional input.
And you could still argue that it's nonlinear, because what's the equation for a heart in 100 dimensions if you are presenting it in this two-dimensional way? Probably something nonlinear, right? Okay, fine. So that's our data set. Let's imagine it's, I don't know, 1950. You're working on this, and you've built that machine now, you've tweaked the dials, and you've given it the data, and this thing is starting to, I don't know, it's starting to recognize the donuts. It's hungry. It's thinking, it's falling in love with you. It's got hearts. It's like, it's definitely capable of original thought. And how does it do this? Well, phone up the aliens from the future, and they give us some code from R. So we run the algorithm. We've got some objective function which we need to optimize. So we go and do that. This is our objective function. So let me just quickly explain. We've got some error function which just counts how many things we are misclassifying. We've got 200 observations. We start out by misclassifying around 140 of them. Okay, and then at each update, what do? We apply our perceptron learning algorithm. We pick an example. We adjust the weight vectors accordingly, and we keep doing that. We just apply our perceptron learning algorithm. Okay, it's bouncing around all over the space. And then eventually what happens? See, it's sort of going down, the error rate going down, the error rate going down, and then it hits 0. Okay, so what does that mean? We've got 100% accuracy on this test. Okay, so this algorithm, this perceptron learning algorithm, our machine little thingy that thinks or whatever, it can score 100% on this, and I can guarantee you, if I showed you all these pictures, some of you would go, "That's not a heart," no, that's and you would fight or something like that. Okay? Yes, were you about to say something?
Well, I was going to say it's overfitting. It's just kind of.
Okay, fine. It's probably overfitting. So how would we fix that? We take out the regularization hammer and we fix things. Yes, exactly. We start fixing things. But okay, so let's say we're not quite there yet, but it's achieving this accuracy. But that's remarkable, right? Because we've got a linear model working on this nonlinear data set, and it's achieving 100% accuracy. How is it doing that?
Similar to how if we have more predictors than we have observations, you can fit anything to anything.
Okay, yes, you're absolutely correct. So why? Let's consider the following. Okay, so again, statisticians thought this wouldn't have been news. This is again from this exact same textbook from Ripley, although from a different chapter. It says the following. How many observations of dimension P can be partitioned perfectly using an algorithm? So this is just binary classification. Well, it turns out the probability that n observations, randomly chosen from any continuous distribution in RP, so it doesn't matter how the data were generated in RP, each randomly assigned to one of two groups, okay, are linearly separable is the following probability. Okay. This is the expression for that probability. Okay, so let's go and what that looks like. Maybe what I should actually show you before I do that. This is what it looks like when the algorithm is learning. Okay. So here's the algorithm learning. We've got 3 weight vectors in this model because it's got 3 different classes. That's the picture it's presented, which is misclassified. And it adjusts each one of these weight vectors to try and detect one of those classes. So each one of these weight vectors is actually associated with a class. And over time, as you let this algorithm run, what you'll end up seeing is a pattern emerge. Okay, I'll stop it and then I'll run it a bit quicker. Oh no, it's pretty much halfway there. Okay. So, which one of these weight vectors is recognizing what? So weight vector 1, that's probably like donuts. It's telling you look at the center, you find anything. Which one is heart? It's probably this one. It says there's nothing in the corners, the heart, and so on. Something like that. Okay, so just to show you what that looks like. Over there. Let's look at the probability of the corner. Why it doesn't want to do this? Okay. This is that probability of being linearly separable as a function of n, the number of observations you have, okay, and the number of input dimensions you have. For our example, we've got 100 input dimensions. Okay, but 100, that's the wrong way around. Yeah, we've got 100, our input size is 100. Can you see up at top there? So this is the probability of being linearly separable, so 0 to 1. Okay. Can you see there's a whole region for which the probability of being linearly separable is exactly 1. That means the data will be linearly separable, regardless of how it was generated. Okay. So essentially, all you need to do is to ensure that your input dimensions are sufficiently large, and then you'll have something which is linearly separable. And it gets worse than that, because we don't strictly require to be perfectly linearly separable the problems that we work with. Even if they are not perfectly linearly separable, if they are close, we can still get away with the linear. Okay, cool. So again, linear machinery, don't get caught up in the metaphor of what's happening. Try and understand the mathematics of what's happening. Okay. Now, broadly speaking, with neural networks, what are neural networks doing? I hope I've convinced you now that they are just a set of basis functions. Okay. So the question still remains: what do they actually do? So we'd like to have a go. It's closely related to this. Okay, so now you don't believe anything anymore. I'm a complete neural net atheist. I don't believe in this stuff anymore. No. Okay, so what are they doing? What is this algorithm doing? Yes?
It's more easier to see like patterns in
Okay, but how does it? So you can construct patterns using these models, but how does it do it?
like the relation.
It finds some relation, but what does it do? It looks in the input space. So what is this model doing? This basic, this very like the genesis of all this. Yes.
Just looking at like probabilities, so like if this like certain slots are highlighted, it's quite likely to be one thing.
Yeah.
So like you add, so like for example with the maps, like there was very high positive weight for the certain parts of the heart. That was like unique to that. So it's like then you take a high probability, so it's pretty likely to classify it as heart. And like the one for the rectangle was so bad, but it just had to be not a circle. So as long as it didn't have like a hole in the middle, as long as it wasn't like lining up those probabilities, then you'd get whatever probability which is. So it just
Exactly. Okay. So you're making a couple of good observations there. One, a lot of those weights are redundant. You could probably get the same accuracy with just a handful of the weight parameters, because why? For the heart, you only need to check the corners at the bottom. There's nothing that tells you everything else you need to be able to. Pictures intrinsically are lower dimensional than what they are written down for us. Okay, so that's something to consider. So we could probably realize away most of the parameters anyway, and get the same accuracy, and then probably better performance out of sample. because we're not replicating information that we've seen. So that's one aspect of it. The other thing is, what are we doing? We've got this high dimensional input space. We're just separating the data. So we've got some plane that we're plotting through the data. Now here we've got a 3-class case, and I've given you 3 weight vectors. So what are those 3 weight vectors? There's 3 planes. So you've got a plane like this, a plane like that, and then a plane like this. And the way you orientate them relative to each other means what you do is in the input space, you create these little convex sets. And each of those sets, depending on how those things intersect with each other, determine which class is associated with that. So that's how it's constructing these nonlinear patterns. Okay. You can use this linear machinery to construct nonlinear patterns if you've got enough of these elements to put together. Okay, so you're creating little regions of the input space which are associated, so there's the association bit, with particular values of the response, the outcome that you want to predict. Okay, so that's all they're doing. The more neurons you have, the more planes you have to essentially rotate, okay, and move around. The more layers you have, the more nonlinear those patterns become. Yes?
With this, is this like one layer or multiple layers? Like
This is one layer, one neuron.
how does it have like all the different weight vectors? If that makes sense.
Okay, so the algorithm here for the multi-class case is slightly different. So in our model previously was calculate the sign of those weight vectors. Here it's take the 3 weight vectors multiplied by the input, do it for each of them, take the max of the 3 scores.
Is that not almost like another layer of like you take like all inputs and gives you a probability and then based on that you say is it this, this or this?
It's more like you have a single layer with like 3 nodes, which have linear activations, and then you take the max of the outputs.
Okay, so it's like 3 nodes, like so it's all
Just
weighted
3
into
output
3
nodes, yeah.
Okay.
Just 3 output nodes,
Yeah.
and you apply the max function to that, whichever the argmax, essentially, which one is the maximum.
So does,
Yeah, sorry, no, go for it.
so does that count as one neuron? Because in my brain, nodes and neurons are like the same thing. So I was like, how
I would say it actually counts as, no, it's semantics, right? Because the argmax function there is a single function applied to the 3 weights. If you're adding those, I don't know. I guess you could argue it either way. Let's lean towards calling it 3 output neurons, but there's no hidden nodes.
Yeah.
There's no hidden nodes. Yeah. Sorry, it was you. Yeah.
Yeah, it's totally separate though. It's on the topic of this one. Could you please just explain this graph again? I'm struggling to conceptualize what it's showing us.
It's showing you the probability.
Yeah.
So that's probability on that axis of being linearly separable. So top here, that's probability of 1. And then it gradually goes down, and then it's probability of 0 of being linearly separable. Okay, now we go, that's the number of inputs you have, and that's the number of observations you have. So can you see that this graph is completely independent of how the data were generated? It doesn't matter that the pattern is nonlinear. If you have enough dimensions for the input space, the probability of being linearly separable is 1.
Mm.
So why should you even start with nonlinear machinery?
Mm.
Okay, so you can sort of see the premise for one of my honors topics. Okay. But the point here is not so much that, I don't believe this stuff. It's just let's just separate where the metaphor and the mathematical machinery and what's happening mathematically versus what's happening in what inspired the actual models and how they worked. Yes, Shred.
There's another issue with these, the fact that they can't really account for different positioning, different sizes of these parts or squares and circles. Because the way that they're finding the sides and corners of stuff ends up being pretty centralized.
Yeah, but look, you'll do some data massaging, and yes, in this case, they were sort of massaged, everything was sort of of a similar scale. Typically, you would do that. I guess if you want to make your algorithms more robust, you would have some pipeline which does sort of bring the thing to the middle, scale it to be the same size, or have the same volume essentially of intensities or something like that. you wouldn't leave that to the algorithm. Then you shouldn't expect good performance. Yes?
Sorry, you spoke about taking the max of the three outputs for summation. Why is the max? Why the max?
It's got to do with how the planes are rotated. So in this input space, so let's say the threshold is on this dimension. If you have a plane going like this, another plane going like that, and another one going like this, then what will happen is on that side, this plane is highest, on that side, this plane is highest. So what you'll do is you'll create what's it called? I forget now what the map's called, but you'll essentially create linear bounds, say 3 linear bounds in the input space, which separates the data. So it's just taking the maps because it's saying where's that plane higher, where is its value larger than the other planes? So is that plane at that point higher than the other planes? I've got an example of that. I just don't know where it is. I'll go look for it and then I'll show you in the next lecture what that picture actually looks like. Okay, cool. So that's perceptron learning. That's the history of neural networks. And what's that? Anyway, in our next lecture, what we're now going to do is I'm going to show you the actual mathematics of neural networks as we know them today. You'll see a lot of the same, or a lot of the resemblance to what we've just done now. And then we're also going to start coding them from scratch. Okay. So we've bought some time. We're going to spend more time on evaluating these neural networks, and on the backpropagation stuff that'll come later.